Alright students, in this video we're going to talk about significant figures, or also called significant numbers, and rules on assigning measured numbers a significant figure and a number. So to start out with, let's talk about a difference between a measured numbers and an exact number. So keep in mind these Sig Fig rules only applies to measured numbers, not to the exact numbers. So exact numbers are actually the ones that comes from the countings. For example, I can have 100 students, so that's going to be an exact number, or I can have 12 bananas, that's going to be an exact number. Some of the definitions are also going to be the exact numbers. For example, there are 12 inches in 1 foot, so 1 foot has 12 inches, so that's by definition. So as a result, that's going to be considered an exact number as well. So anytime you have an exact numbers, it doesn't matter how many digits you have, they consider to have infinite amount of sig figs. So they got infinite sig figs on them. However, when we have a measured numbers, we have to apply some rules on assigning the sig figs, and a measured number is going to be something. It's going to be a number that's actually received after using a tool. For example, I can use a metric ruler to determine the length of the table, and let's assume the length of the table comes out to be 22.56 centimeters. So that's going to be your that's going to be your measured number. And then assume I'm measuring the mass of something. So to measure the mass of something, you can use the triple beam balance, or you can just use the weighing scale. And assume the weighing scale gives you the mass of an object to be 5.967 grams. Okay, so these are actually going to be your measured numbers. And one more thing you want to keep in mind, the very last digit you always going to have in a measured number is considered to be the estimated digit, also called an uncertain digit. All right, and that uncertain digit usually comes from the estimation. It does not reflect the markings on the tool or on the metric ruler in this particular case. If you have a digital balance, like in this case, if you measure the mass of something to be 5.967, so obviously you're not really using any tool to measure the mass, but it's in a balance that actually reads the mass for you. It's a digital balance. So even in a digital balance, the very last number that you see in there is considered to be the estimated. In this case, it's going to be the 7, the estimated digit, and in the case of the length, the 6 is going to be considered your estimated digit. Okay, well, in those measured number, there are some numbers, in the measured number, there are some digits that are considered to be significant, and there are some digits that are not considered to be the significance. So there are actually some rules on assigning the sig figs on a measured number. So keep in mind that only applies to the measured numbers, not to the exact numbers. So the first rule is, if you see any non-zero digit in a measured number, it's going to count it as a sig fig, okay, or it's significant number or a significant figure. Assume I have 77, and assuming that's in a measured number, it's going to have 2 significant figures. Assume I have 956, so it's got 3 digits on it, all of them are non-zero, so it's going to have 3 sig figs. Okay, well, this is actually 0. However, the problem steps in whenever you have zeros in these numbers. Okay, so there are times when you count the zeros as sig figs, and there are times when you don't count these zeros as sig figs. So let's look at the rules when you count the zeros as your sig figs. If you have a 0 between a non-zero digits, then they will count as sig figs. For example, I could have 707. So now this 0 is in between the non-zero digits. It's going to be counted as sig figs. So it's going to be 3 sig fig in this particular number. Or let's assume I have 500097. Now in this particular case, all these 3 zeros are in between the non-zero digits, so they would be counted as a sig figs. Now keep in mind the zeros doesn't necessarily have to be right after a non-zero digit or right before a non-zero digit. As long as you have a non-zero digit before and after, they would count at those zeros would count as sig figs. So in this case, we have everything counts here. So we got 1, 2, 3, 4, 5, 6. So we got 6 sig figs in this particular number. Okay. Well, there are gonna be zeros that are actually after a non-zero digit, but then they are either before or after a decimal. They would be counted as sig figs. Those are also called the trailing zeros. The zeros are going to be the one after a non-zero digit are called the trailing zeros. And in this case, these trailing zeros are in the presence of a decimal. So as long as you see in a decimal in a given number, the trailing zeros do count as the sig figs. Let me take an example here. So assume I have 957.00. So those zeros are after the non-zero digit, which is 7, and they are also after the decimal, so they would count as a sig fig. So in this particular case, I have 5 sig figs. Okay, what if you have something like 957.00 point? Now, again, these zeros are still the trailing zeros, but there isn't a decimal after those zeros, so they would count as your sig figs. Keep in mind, as long as you have a decimal in the trailing zeros or in a number that have the trailing zeros and contain the decimal, those trailing zeros would count as the sig figs. Okay, well, let's talk about the zeros that actually do not count as sig figs. If you have the trailing zeros without the decimal, then they would not be significant. For example, if I have 957.00, now I don't see any decimal in this number, so since there's no decimal in this number, those zeros would be insignificant or not significant, so we'll have 3 sig fig in this particular number. Or what if I have an example that looks like this, 9057000. So what do you guys think, how many sig figs I have in this particular number? So I do have 3 trailing zeros, so the zeros after the non-zero digit, which is a 7. So those zeros are not going to be counted as sig figs because there's no decimal involved in the number. Okay, and then what about the 0 that's between the 9 and 5? Well, that goes back to rule 1, where we have said if you have a 0 that's between the non-zero digits, that would count as a sig fig. So in this case, it's going to be 4 sig figs. Okay, so those are the trailing zeros in the absence of the decimal. They are not counted as a sig figs. Okay, and then what if you have zeros that are actually before the non-zero digits, and they could be either after or before the decimal? They're also called the leading zeros. The other name for those are space holding zeros. So those leading zeros or the space holding zeros are not significant. Assume I have 0.0075. So in this particular case, the zeros before the non-zero digit 7, I got 3 of them. And then I do have a decimal there, so it doesn't matter if the 0 is before the decimal or after the decimal. As long as they are the leading zeros or just the space holding zeros, they are not going to be counted as sig figs. In this case, it's just going to be 2 sig figs. Okay, well, these are the rules for the sig figs. Let me take a couple of examples here that sums up everything actually. What if I have a number that looks like this? 50500.0. Okay, so then how many sig figs we got in there? Okay, so this zero that's between the fives will count as a sig fig because it's in between the non-zero digits. Okay, these last three zeros are going to be your trailing zeros, and since these are the trailing zeros with the decimal, they would be designed assigned as a sig figs. So everything counts as a sig figs here. So that means I'm going to have 1, 2, 3, 4, 5, 6 sig figs in this particular number. Okay, what if you have something like 6.504000? Okay, so how many sig figs in this particular case? Okay, well, obviously all the non-zero digits counts as sig figs. This zero that's between 5 and 4 will be counted as a sig figs because it's between the non-zero digits. And now these last three zeros are your trailing zeros. Now, these trailing zeros are actually after the decimal, or there isn't a decimal involved in the number. Now, keep in mind the decimal does not necessarily need to be right before the zeros or in the zeros. It could be anywhere in the number, and it kind of satisfies that requirement that these are the trailing zeros in the presence of the decimal. So everything counts as a sig fig in this. So that means I'm going to have 7 sig figs in this particular case. Okay, well let me take another example. What if I have 0.005060700? Then how many sig figs in this particular case? Okay, I got two zeros that are in between the non-zero digits, so that's going to be that 0 and that 0, so they will be counted as a sig figs. All right, so those are out of the question. And then I got these space holding zeros are also called the leading zeros. So the leading zeros are never sig figs, so those are not going to be counted as sig figs. Well, what about these last two zeros right there? Those are your trailing zeros, but then those are the trailing zeros in a number in the presence of a decimal. So your decimal is way before, but there isn't a decimal. That's all it really matters. So since there isn't a decimal, these trailing zeros count as a sig figs. So what I'm looking at in terms of total sig figs here, all these numbers from 5 all the way to this last 0, all these digits will be counted as a sig figs. So I got 7 sig figs in this particular case here. Okay, so that's how you're going to be doing the sig fig rules. Now, when you're doing the calculations, you have to be a little bit careful about the sig fig rules, how many decimals you can keep or how many sig figs you can keep and so on. So there's actually two rules you have to really worry about. One rule involves when you're actually doing the multiplications and the divisions, or a combination of both. You could have just the numbers being multiplied, or you could have just the number being divided, or you could have both of those. So anytime you see that condition, you are looking at you are looking at so-called an least sig fig rule applied. Okay, what that really means, your answer should contain a least number of sig figs as that of a number with the least sig fig in the question. So that may sound confusing, but just keep in mind you are looking at the least significant numbers in this particular case. So your answer should have the least number of sig figs possible. So to actually solve that, first of all, you actually want to go ahead and put those numbers in your calculators and see what that comes out to be. So let me just go ahead and put those numbers in the calculators and see what that comes out to be. So I got 2.00 times 0.043 times 20.00 times 0.3 times 19.6. So this comes out to be 10.1 1136. So when you do use your calculator to solve these, to multiply these numbers or divide these numbers or even add or subtract these numbers, the calculator really doesn't think of sig figs. It will just give you the best possible answer you can come out with in terms of keeping all possible sig figs, including multiple decimal places. Now, since all you're really doing here is just multiplying the numbers, since you're only multiplying the numbers, you have to look for the least sig figs in the question. Okay, so let's go back here and figure out how many sig figs we got in each of those numbers. So this 2.00 has how many sig figs? Well, those are the trailing zeros in the presence of the decimal, so that means that's going to be 3 sig figs. What about 0.043? So those are your leading zeros, and leading zeros are not going to be sig figs, so that means what you're really looking at is these last two digits, so that's your 2 sig figs. 20.00, okay, well those are your trailing zeros in the presence of the decimal, so everything counts here, so that's going to be 4 sig figs. What about 0.30? 0.30, the zero in front of the point is your leading zero. That's not going to be counted as a sig fig. However, the zero after 3 would be counted as a sig fig because that's your trailing zero in the presence of the decimal. So that's 2, and 19.6 is going to be 3. All of them are non-zero digits. So now you have figured out how many sig figs you have in all of those numbers here. So that means the lowest number of sig figs is actually 2. You got two numbers that has 2 sig figs in there. So that means your answer should not contain more than 2 sig figs. So that's all we're really looking for here. Now, I want to somehow change this number to 2 sig figs. And this is where I gotta use my rounding rules as well. So the 2 sig figs that will be made in this particular number is gonna be 1 and 0. Okay, so those are, though they will make 2 digits in there, and you want to make sure those two digits will count as 2 sig figs at the end of the day. Now you're going to be dropping the rest of these numbers. So when you're dropping this, the rest of these digits right there, so the very first digit that's being dropped, if that digit is more than 5 or more than 5, then the very last digit that you're going to be keeping goes up by 1. If the very first digit that's being dropped is less than 5, then you leave the very last digit that you're keeping as it is. So in this case, you have 1 here, so this is less than 5, so that means you're going to keep this 0 as 0. So it's just going to be 10 at the end of the day. So think about this. If you buy something for $10.11, for example, for the most part, you're just going to say it's $10. All right, so that's how you're going to be using the Sig Fig rules. If you buy something for $10 and assume 60 cents, there's a likelihood chance that you will round that up to $11, that if that particular material is $11. So the rounding rules are based on the 5. If something is 5 or bigger, then you keep the very last number, you increase the very last number you're keeping by 1. If the number you're dropping is less than 5, then you leave the very last number you're keeping as it is. So in this case, if you leave this as 10, there is a problem with it. Well, this 10, this 0 after 1 becomes the trailing 0 in the absence of the decimal, so that means that's not going to count as a sig fig. So if you leave this answer as 10, that will be counted as an incorrect. So make sure you actually put a decimal after this. So when you put in a decimal after this, now this becomes a trailing 0 in the presence of the decimal, so that will be actually 2 sig figs at the end of the day. Okay, so that's how you're going to be doing the multiplications and divisions, and you're going to be using the least sig fig rules there. Okay, let's look at when you're actually adding and subtracting the numbers. So when you're adding and subtracting the numbers, you actually don't use the least sig fig rules, but rather you use the least decimal places rule. Everything else stays the same. You want to make sure you keep Your answer should contain the least number of decimal places possible. So that's the shortest way of saying it. Now, assume I have this mathematical problem where I'm adding and subtracting some of these numbers. So let's just go ahead and plug those numbers in the calculator and see what that comes out to be. So I got 0.458 plus 0.98 plus 10.98 minus 5.786 and then plus 11. So this comes out to be 17.632. So all we're really doing in this particular question is either adding or subtracting. So you want to look at your decimal places. So the first number has 3 decimal places. Okay. The second number has 2 decimal places. The third number has 2 decimal places as well. The fourth number has 3 decimal places. And this last number, which is 11, has 0 decimal place. So based on this rule, we should not have any decimal places. So that means this 17.6 will be rounded up to 18. So remember this first number that we're actually dropping, which is going to be 6, is actually bigger than 5. So that means the 7 is going to go up by 1 and it becomes 8. So you don't want to have any decimals. So this is how your answer is going to look like. It's just going to be 18. Okay, so that's the rule when you're adding and subtracting numbers. Okay, let's talk about scientific notation. So, well, the scientific notation is actually a way of writing a very small or a very big number into a form that can be easily read. Now, let me give you an example. Assume I have a number that looks like this. I got 0.0000569 okay, and the question is telling you to change this in the sign notations with 2 sig figs. Okay, now worry about converting this number into 2 sig figs later on. If you look at right now how many sig figs we got, well, all these zeros are actually leading zeros, so that means we have 4 sig figs momentarily, but this is something you want to worry about later on. First, you need to change this into a scientific notation, and here is the rule for the scientific notations. Your decimal needs to be after the very first non-zero digit. Well, your very first non-zero digit in this case is actually 5, so that means you want to move your decimal after the 5. Okay, so when you move it, you want to count how many points you're moving to get, how many positions you're moving to get to after non-zero digit 5. So it counts 1, 2, 3, 4, and 5. So it seems like you're moving this decimal 5 places to the right side in order to get between 5 and 6. So it's going to be 5.698, and your scientific notations are written in the form of 10, so it's going to be times 10 to the power. So now count how many times you have moved this decimal to the right. So it seems like you moved it to 5 places to get to after 5, so it's going to be 10 to the 5. Now this is where students get really confused, when to put a negative 5 and when to put a positive 5. Now here is a simple answer to that problem. If you're dealing with a number, when I say a number, it means an original number that's given you. If that number is less than 1, then you put a negative as in power. If the number is more than 1, then you put a positive. Now this particular number that was given in the beginning is 0.0000569 is clearly less than 1. So when you're writing the scientific notations, any number you get as in a power of 10 is going to be a negative number. Okay, so this is going to be the scientific notation for that. Now the next task we have to do is change that to 2 sig figs. So when we're changing this to 2 sig figs, we're looking at this 5 and 6 making those 2 sig figs. So that means we need to drop the 9 and 8. So the very first number that's being dropped is actually 9. That's bigger than 5. that means this 6 that we're keeping is going to go up by 1. So this answer will become 5.7 times 10 to the minus 5. So that's going to be 2 sig figs in this particular case. Keep in mind this 1 in the 10 does not count as a sig fig. That's just a way of representing the scientific notations, but this 1 in the 10 don't count that as a sig fig. Okay, so that was actually a smaller number. What if you have a big number? So assume I have 2685000. Okay, and we're asked to change that to scientific notation with, let's assume 3 sig figs. Okay, well, right now, if I count how many sig figs I have, I don't really see any decimal in this particular number. So that means these last 3 zeros are going to be called trailing zeros, and without the decimals. So that means these first 4 non-zero digits will count as a sig fig. So that means that's going to be 4 sig figs you got in there. Now, I want to change that to the scientific notation, but I don't really see any decimal here. Okay, so whenever you don't see any decimal in a given number, you want to assume it's actually at the very end. So your decimal in this particular case is going to be after those 3 zeros right there. So this is more like an assumption that you just assume it's at the very end if you don't see one. Okay, so then what's the rule for scientific notations? Your decimal should be after the very first non-zero digit. Now, what's the very first non-zero digit here? It's actually 2. So you want to make sure you move this decimal all the way to after 2. So then I want to count how many points I'm going to be moving to the left in order to get to after 2 here. So it's going to be 1, 2, 3, 4, 5, and 6. So it seems like I'm going 6 points to the left in order to get to after 2. So I'll go ahead and write down 2.685 times 10 to the power 6. Okay, so now whether you want to keep it positive 6 or negative 6, this original number that's given is actually bigger than 1, so that means I want to have a positive 6 there. Okay, so that's how you're going to be converting this to scientific notation. The next task you will have is to convert this to 3 sig figs. Your 3 sig figs will be made by the time you get to this 8 here, because this 2, this 6, and this 8 will make a total of 3 sig figs. That means I need to go ahead and drop this 5. Now, when I drop this 5, it's going to be okay, so when I drop this 5, since this is 5, I have to increase this 8 by 1. So this is going to be 2.69 times 10 to the 6. All right, so that's how you're going to be converting this number into a scientific notation. Now, there are times when they ask you questions like, okay, what if you want to change this particular number into 3 sig figs, but not writing in the form of scientific notation, but just changing into 3 sig figs. When I want to change this to 3 sig figs, so let me just go and write down this original number. That's 2685000. And if I want to change this to 3 sig figs, I would go ahead and write down, I need to drop this 5 because that's the last digit that's going to be counted as your sig fig, and that would make it 4 sig figs. So I need to get rid of this 5. So when I'm dropping this 5, this number, that's this digit that's before the 5, will go up by 1. So the rule still stays the same. So this becomes 269. But then don't leave it like that. Don't just drop all these numbers as it is, because writing this 268,5000 and writing this 269 is a very big difference. So you're changing the magnitude of the number. You want to make sure you don't change the magnitude of the number, but when you write down, when you go ahead and make this 8, 9, meaning you getting rid of this 5 in the form of the 0. So this 5 actually becomes 0. So now you're going to have 4 zeros instead. So now this number right there, this is like 2690,000, and this 2685,000 is roughly the same. All right, so I hope that helps, and I'll have some more videos posted.